Okay. So, actually so that brings us to the next question of how do I actually implement this in FDTD. Okay. So, let us take a definite case. Again, this is my boundary and I am showing you one E cell. Okay, let us make it bigger. So, this is the right boundary, okay. That means there is nothing beyond this boundary and I am taking a simple 2D TM polarization case, okay. And what do I want to do is want to impose which component of electric field should this be applied to in the ideal case? Which is the field on the boundary? Ey, right? Ey is the variable that is lying on the boundary, so I have to impose the boundary condition on Ey. Okay. So, we want to impose this in FDTD. Okay. So, you see the challenge now. Ey is tangential to the boundary, but imagine a plane wave that is travelling towards the right boundary. The k vector is going to be perpendicular to the wall, but where is the electric field? Electric field is transverse, right? Consistent. Right. How would you do this? See, what you are trying to do is you are trying to impose this condition at which point? Over here. So, there is a space derivative and there is a time derivative. How will I calculate the space derivative by finite differences? Can I do it? So, one possibility is that I can take a backward difference. Instead of a centered difference depends on some value to the right and some value to the left, I subtract those two. Here I can't do that because it is the end of the domain, I have nothing to the right of this. So, I can't do centered difference. So, one possibility is I do a backward difference in space. I can still do centered difference in time, right. But what is the disadvantage of doing a backward difference? Error increases. As it is, this boundary condition is going to introduce error. Then on top of it, my imperfect way of doing finite differences will give further. So, I could do backward difference, but error is high. Okay. So, the compromise that we do is this: use center differences. So, use but I can't do center differences. So, because there is nothing, there is no variable stored to the right of this boundary. So, then I impose it, use center differences, but impose this half a cell inside the boundary. If I impose this, so for example, at the location of xz. So, I am going to impose this boundary condition. Technically, I should be on the boundary, but doing that has this problem of backward difference. So, I say okay, let me just apply this boundary condition in the middle of the cell rather than at the end of the cell. So, that I have a value on the left and the right, I can do center difference. So, that is a compromise solution. It is not a golden rule that you have to do this. If you really wanted to, you could do backward difference also. Okay. Both will have some trade off in terms of errors. You will have to update the EY value. Yeah. So this whole implementing in FDTD is how do I update EY on the boundary. So that's what we are trying to arrive at. Okay. Yeah. So I'll tell you what I mean. So dE by dx, that's the first term to apply dEy, right? How do I implement this? So I'm saying instead of taking the backward difference, I take center difference. Center difference I can only take between the values that I already have, right? So EY on the left and EY on the right, and subtract these two. But what I do is dEy by dx, I am going to take the average over two time instances. So I am going to find out this finite difference not at just time instant n, but also n minus 1 and take the average to reduce this error, because I am imposing it in the middle of the cell, not at the boundary. So I want to minimize that error, so I take an average. So it is going to be the average over here. So EY n plus 1. So center difference, okay. So let us call this point over here as I comma j. Okay, so this is going to be what? What are the locations of EY in the center difference? I, j plus half, right? Next is going to be EY, the same instance, then n plus 1, and now what should I write? This is dEy by dx, so it should be a finite difference in x. It cannot be I plus 1, there is nothing, I plus 1 does not exist, I minus 1, j plus half, that does not change, right, divided by delta x. This was a time instance n plus 1, so I will, this is center difference. Yeah, I am taking the difference between I and I minus 1. So this approximation is correct at I minus half. That is why I am saying that the compromise is to use center differences, but that makes the relation to be most accurate in the center, middle of the cell. If you did backward difference, then it would be, yeah, I can also interpret this as a backward difference. So the next term over here is just the same expression, but at time instance n, right. This is sort of done to reduce the error, so everything else remains the same. dE delta x. Now dE by dt, I will average its value over space. Same philosophy, I want to minimize the error. Okay, so the first term I am taking time difference. So EY n plus 1, okay. Location will be, what will the location be? Remember, I am taking time differences. So this, what should the next term be? EY n, very good, and location? Same location, because I am only taking a time difference, divided by delta t. I want to average this difference to minimize the error. So I will take the average at, again, n plus 1. Now what should I write over here? I minus 1, exactly, I minus 1 j plus half minus EY n plus 1 I minus 1 j plus half. Okay. So with the result, both of these expressions, this and this, are being evaluated, are most accurate here, right, in the middle of the cell. The first one obviously, and the second one also, right. I am taking the average of something from here and something from here. So, it is more accurate in the middle of the cell. So, that is the meaning of this compromise. I am using a center difference, I am interpreting it as a center difference, but it is being, by doing this averaging, it is being imposed half a cell inside the boundary. Yeah, this should be N, sorry. Everything else is alright? Okay. So, advantage was accurate to second order, right, because it is a center difference. Okay. So, this is what we will substitute for Ey into this boundary condition, and in any sort of what do you call implementation, we want to get an update equation out of it, right. So, what will we do? It is a center difference. Center difference is accurate to second order in H, the spacing between the points, that is what I mean, and forward difference or backward difference are only accurate to first order. It is the power of the error, we had done that in the beginning in finite difference. Okay. So, now what do? We will take these guys, each of these expressions. So, I take this guy and substitute them here, right, and what will that give me? It will give me some update equation, right. What is the term that I need to update from these various terms? Which is the term that I really need to update? Which I do not know. I mean, everything else I know. For every E, Y inside the domain, I have my usual FDTD update equation. For what term do I not have an update equation so far? The Ey on the boundary, right. So, that is Ey n plus 1 I j plus half. Okay. So, substituting too many t's, right, to get so what do I get? So, I will write down, it is very simple, right. There are how many 4 terms and 4 terms, 8 terms, right. So, what will be the key? Keep the term that you want on the left hand side, move everything else to the right hand side. Okay. So, I will write down the final expression. So, there is a term gamma comes which captures a lot of the constants. I will just write down the final expression and then tell you what this is. I am looking for Ey n plus 1 I j plus half, yeah, that is what I want, because that is the guy on the boundary. Gamma is going to be equal to 1 minus alpha by 1 plus alpha, and alpha is my usual Courant parameter. Okay. So, this is an update equation purely in terms of Ey's at various different locations in space and time, right. So, in order to get this, I also need at the same point over here, I need this, right. So, this is the same point in space. I need the electric field on the boundary at a previous time instance to update it at the present time instance, right. The only thing that is different between these two guys is n and n plus 1. Okay. The other guys, these are being updated by how? They are on the interior, right, I minus 1. So, this is from usual update equations. Okay. So, how can we update this? There is a little bit of a trick here now, right? I mean, there is a little bit of a catch. I need to know this guy to begin with. Only if I know it at a previous time instance can I use this update equation in the future. So, how will I, what is the way out of this problem? How will I know it in the beginning? No. The problem is that in order to get the field on the boundary at some time instance, I need to know the value of the field on the boundary at a previous time instance. So, how do I know it in the very first place? At the beginning of the simulation, what do I know it to be? 0, right. So, typically what has happened is, let us say this is my computational domain over here, this is some antenna, some object over here. At time t is equal to 0, none of the fields have reached the boundary, right. We are stepping in time. So, the field is slowly hit the object, then is travelling outwards. So, at time t is equal to 0, very safely I can set the Ey's on the boundary to be equal to 0, right. So, set Ey 0 equal to 0. Initial conditions on the fields I can set to 0. I mean, that is a typical way. If you have a specific reason to set it to something else, you could do that. But if I am turning my source on at time t is equal to 0, right, then of course the field has not reached anywhere. I will set everything to 0, right. Yes. So, actually when you do these calculations, you can store the field values at every time snap. So, you can see very beautifully field is travelling outwards in whatever direction. So, you can visualize multiple scatterings happening and then finally reaching a steady state value. In your FEM and integral equations, you do not get to see that beauty, you just get final steady state solutions, right. Okay. This is reasonable in most cases, reasonable. Okay. So, what we have looked at is how to take your absorbing boundary conditions and implement them in FDTD, and for that we need to take care of our very initial conditions, right. So, if this is clear, then we will, to conclude this module, I'll just mention one very simple way of making your boundary condition accurate for higher order. Okay. So, what was the boundary condition that we had imposed first? D by dx plus 1 by c d by dt Ey is equal to 0. This was first order ABC. Now, supposing I say I want the reflection to go to 0 at not just one angle, but two angles. So, the key is to play around with this expression. This is what I am imposing. So, I generalize this to, I will just write the expression and then we can work it out later why this is correct. One expression and another, since it is second order, there will have to be two terms. So, we are not actually going to implement this in this course, but I just want to give you the high level idea. So, if you do the same analysis that we did, a rightward, I mean a wave travelling at some non-normal direction and calculate the reflection coefficients, what you will find is that if I plot the reflection coefficient over here versus theta 1 and theta 2 over here, what happens is that you get nulls like this. Okay. So, these are called Higdon boundary conditions, named after the scientist who. Okay. So, that concludes our discussion of higher order I mean, how to implement first order ABCs and just a high level idea of what to expect in a higher order